The universe is filled with countless other worlds. Among the thousands of exoplanets discovered beyond the solar system, none can yet be considered more hospitable to us than Earth. With some melted by the unbearable heat of nearby stars, others are forever encased in ice or scorched by devastating radiation. But among the many inhospitable worlds, there are others that are quite different. There are great waters of oceans and rivers on their surface. Clouds float across their sky, and showers and thunderstorms rage in their atmosphere. Perhaps these worlds can become the cradle for beautiful and unique life, as has once happened on the Earth. And today, we're going to visit some of the most remarkable of them. It can hardly be disputed that life is one of the most amazing, complex, and mysterious phenomena in the universe. Despite the fact that we've been studying it for thousands of years, many important questions about it still remain unanswered. And the greatest among them is, how widespread is biological life beyond our planet? At this point, we cannot yet say with a satisfying degree of certainty whether the Earth's biosphere is a unique phenomenon, or whether it has emerged as a natural and logical result of continuous evolution. It is hardly surprising that the search for life beyond Earth is one of the most important fields in science. And in order to identify the most promising celestial bodies in this respect, the so-called Earth Similarity Index, or ESI, is used. It is based on two main parameters: the level of gravity on the surface of a celestial body and its equilibrium temperature. It is these parameters, according to scientists, that determine how much the other world can be similar to Earth and how favorable the conditions on its surface are for hypothetical life. The undeniable advantage of the ESI is its simplicity, because when an exoplanet is discovered, you can usually determine its proximate orbit, mass, and size, and this information is just enough to calculate the basic parameters of the index. However, for all its appeal, it does not take into account many factors critical for sustaining life. Therefore, we will allow ourselves to be as presumptuous as to formulate our own evaluation system, taking the ESI as the basis and supplementing it with several important parameters. The activity of the parent star can be singled out as one of them. It is known that frequent flares and stellar matter ejections characteristic of red dwarfs can adversely affect the stability of the atmosphere and radiation background of the nearest exoplanets. Nevertheless, red dwarfs are considered more favorable than large stars, like Sirius or Vega, because the lifespan of giant stars is too short, and the radiation is too destructive, leaving no chance for potential life to develop. The most favorable ones are orange and yellow dwarfs, including our Sun. The probability of tidal locking is another significant factor to be reckoned with. This probability depends on the distance between an exoplanet and its star. Celestial bodies located too close to their stars permanently face them with one side only. As a consequence, there is a large temperature difference between their day and night hemispheres. Too great a distance from the source of heat and light puts the planet outside the habitable zone, which drastically reduces the chances of the genesis of life. It is also necessary to consider the type and chemical composition of a given exoplanet, because in order to develop, hypothetical life requires a certain set of chemical elements, in combination with characteristic relief. Such conditions can be seen on rocky, terrestrial-type planets, or super-Earths. Mini-Neptunes, meanwhile, do not have solid surfaces, and ocean planets are deficient in many elements. Thus, the set of parameters we have specified allows us to comprehensively assess how favorable the conditions on a given exoplanet are for hypothetical life. For example, in a scheme like this, the Earth looks extremely attractive against these parameters, being the natural benchmark for other objects. At the same time, Mars although it has the highest similarity index to our planet in the entire solar system, has a number of obvious disadvantages. It is too cold, too low mass, and demonstrates a significant water deficit. Venus, on the other hand, despite appearing very similar to Earth on the face of it, is too hot because of the strong greenhouse effect. And although most of its parameters are in the green zone, the extremely high temperature is a critical disadvantage of the planet, effectively cancelling out all its advantages. Thus, there are no planets within the solar system sufficiently similar to Earth to be considered favorable for life. However, beyond its boundaries, more than 5,000 other worlds orbiting distant stars have already been discovered, and in many respects, some of them can be considered similar to our planet. One of these objects, closest to us, is an exoplanet known as Kepler-452b. It is located just 15.2 light-years from our planet. It was discovered in 2022 using the radial velocity method. This method is effective for finding relatively close exoplanets and involves capturing subtle fluctuations of the parent star caused by the movement of space objects around it. The exoplanet is located near a small and dim red dwarf known as Gliese-1002. Its radius is only 14% that of the Sun, and its mass is 8 times smaller than that of our star. Given that Gliese-1002 has a surface temperature of just 3000 Kelvin, or about 2730 degrees Celsius, it is not surprising that its luminosity is extremely weak. It's about 700 times weaker than the Sun's. Observations also show that the object is quite serene, which is unusual for stars of this class. Due to the low luminosity of this red dwarf, its habitable zone has an extremely small radius and width. However, the object Gliese-1002b is located near its outer edge and can be considered potentially habitable. According to observations, this celestial body completes a full orbit around the center of its system roughly every 10 Earth days. Consequently, the average radius of its orbit is clearly very small and is about 0.046 astronomical units. It is assumed that because of the extreme proximity to the parent star, the exoplanet is likely to be tidally locked, facing it with one side at all times. Calculations show that the celestial body receives 1.5 times less energy from its star than Earth does from the Sun, and its average surface temperature could be approximately 230 Kelvin, or 43 degrees Celsius below zero. Incidentally, it is slightly warmer than Mars. Given tidal locking and a possible greenhouse effect, this means that liquid water could be found in the exoplanet's surface, and thus there may be conditions for sustaining life. At least some terrestrial organisms are able to survive in such conditions. Calculations also show that the mass of Gliese-1002b is 8% greater than that of our planet, and the radius exceeds the Earth's radius by only 3%. Using the data, it is not difficult to determine the acceleration of freefall on the surface of the celestial body. It practically does not differ from the value we're used to. Thus, the combination of all known factors suggests that Gliese-1002b is a rocky planet, most of which is covered with ice. Due to its size, which is very near to that of the Earth, it has a rather high ASI of 0.86, and in our scheme, this object would look like this. At the same time, modeling of the planet's climate shows that its illuminated hemisphere can receive enough energy to support an ocean of liquid water, with archipelagos of islands or even fully fledged continents. Also, tidal deformations caused by the nearby star warm up the planet's interior, so the existence of an ocean hidden under the ice, even on its night side, shouldn't be ruled out. Incidentally, Gliese-1002b is not the only planet in the system. It was discovered alongside another object dubbed Gliese-1002c, which is located a little further away, namely at a distance of 0.074 astronomical units from center. A full annual rotation takes this exoplanet 21 days, and its mass exceeds the Earth's by about 36%. The object receives 4 times less energy from the parent star than our planet does from the Sun. So the temperature on its surface is quite low, just about 182 Kelvin or 91 degrees Celsius below zero. If we use the previously developed scheme, then this exoplanet will look like this. It can be assumed that the conditions on the surface of Gliese 1002c are close to those observed on the satellites of Jupiter or Saturn. Increased volcanic activity caused by the planet's high mass could lead to the formation of a hidden ocean, with warm and salty water, rich in many chemical compounds. Hypothetically, life could also develop in such conditions, possibly in highly unusual and unexpected forms. Of course, among the great variety of known exoplanets, much warmer and more favorable worlds can be found. Such, for example, is the planet K2-72e, located 217 light-years away. It orbits a small red dwarf, about 4 times less massive than our star. Its radius is 0.33 of the solar radius, and its temperature is relatively low, reaching 3,360 Kelvin, or about 3,100 degrees Celsius. Observations made by the Kepler orbiting telescope showed that the exoplanet crosses the disk of the parent star every 24 days. This means that the radius of its orbit is very small and is about 0.1 astronomical units, which implies that the celestial body is located within the habitable zone and can be considered potentially favorable for harboring life. According to the received data, it is also suggested that K2-72e may be tidally locked or in orbital resonance like Mercury. Despite the star's low luminosity, the exoplanet receives 11% more energy than Earth does from the Sun. Assuming that the atmosphere of K2-72e is similar to Earth's, the average temperature on its surface should be about 295 Kelvin or 22 degrees Celsius above zero, which is slightly warmer than on our planet. At the same time, it is worth remembering that if the celestial body is tidally locked, there is a high probability of extreme temperature variations between the day and night hemispheres. In addition to this, it must be taken into account that its parent star, like most other red dwarfs, is erratic and is often observed to flare up and emit great amounts of stellar matter, which can be detrimental to the atmosphere and surface of nearby space objects. Calculations show that K2-72e is 29% larger in diameter than the Earth and is about 2.2 times more massive. Knowing this, we can calculate the level of gravity on the surface of the celestial body. It is about 32% higher than we're used to. Thus, with all the known data taken into account, we can assume that this exoplanet is more likely than not a rocky super-Earth, where liquid water and a dense atmosphere can be found. Its Earth Similarity Index is quite high, and is 0.87, and in our scheme this object will look as follows. Planets of this type are expected to have a wide variety of chemical elements, and their relief should be smooth and favorable for the origin of life. Undoubtedly, the frequent flares of a nearby star pose a tangible threat to the atmosphere, but a powerful magnetic field will hypothetically deflect stellar wind particles, and the oceans will protect their inhabitants from this destructive radiation. In this case, we can assume that on K2-72e, it is possible to observe incredible auroras, by far more impressive ones than on our planet. As for the hypothetical biosphere that could develop on such a planet, it would likely be markedly different from Earth's. A different spectrum of incident light might force local plants to use alternative substances for photosynthesis, so their leaves would likely be purple or reddish in color. In addition, excessive radiation hazards may be an obstacle for life forms to venture on land. Alternatively, it may lead to the evolutionary formation of defense adaptations, such as thick skin or specific cellular structures. Similar features are known to manifest themselves in some terrestrial organisms, such as tardigrades, archaea, and some fungi. Meanwhile, in addition to this planet, so attractive in many respects, 3 other planets have been discovered in the system. 2 of them, dubbed K2-72b and K2-72c, are located very close to the parent star and are slightly larger than our Earth. It is assumed that due to the emissions and stellar wind of the nearby star, they are devoid of any atmosphere and are similar to Mercury. The 3rd planet, K2-72d, is estimated to be comparable in size to Earth, and its orbit has a radius of about 0.08 astronomical units. It completes a full orbit around the center of the system approximately every 15 days and is located near the inner edge of the habitable zone. Because of its high temperature, conditions on its surface are likely to be close to conditions on Venus, and the probability of the genesis of life is extremely low. In any case, research on this system is still going on, which means we have much to learn about it in the future. Incidentally, all the objects we have looked at here are similar in size to the Earth. However, life is known to be able to adapt to a wide variety of conditions, including high gravity, which is inevitable on massive planets. If we travel about 1,800 light-years away from the solar system, we can find a yellow dwarf with parameters very similar to those of our Sun. It's called Kepler-452, and it's a main sequence star, just 3.7% more massive and 11% larger than the Sun. In 2015, an extremely remarkable exoplanet named Kepler-452b was discovered near this star using the transit method. High-precision measurements allowed us to calculate that it's located at a distance of 1.04 astronomical units from the center of the system and completes a full annual rotation every 385 days. This location renders the probability of tidal locking of the celestial body extremely low, which is undoubtedly a favorable factor. According to the available data, the object Kepler-452b is about 5 times more massive than our planet, and its radius is about 1.5 times bigger than Earth's. This means that the acceleration of freefall on the surface of the celestial body is 2.2 times higher than we're used to. Such a high level of gravity likely helps the planet retain a dense atmosphere and also smooths out its relief, which could lead to the formation of numerous shallow and warm seas. Such conditions are thought to be the most favorable for the potential origin of life, but gravity this high would be extremely uncomfortable for humans. It is also known that Kepler-452b receives 10% more energy from its parent star than Earth does from the Sun, and is in its habitable zone. Calculations show that the average surface temperature of the object is about 300 Kelvin, or 27 degrees Celsius above zero, which is 11 degrees more than on our planet. This means that the climate of Kepler-452b may be close to that of the Earth's Mesozoic. However, with a certain composition of the atmosphere, this temperature may be dangerous and may lead to the acceleration of the irreversible greenhouse effect to the point of complete vaporization of the oceans. According to some hypotheses, it was a process of this kind that tragically changed Venus several billion years ago. With all the known factors combined, we can assume that Kepler-452b is most likely a rocky super-Earth, rich in a wide variety of elements and minerals. It is believed that because of the increased content of radioactive elements, a planet of this type should exhibit increased volcanic and tectonic activity, and its high gravity should prevent the formation of extremely high mountains and deep chasms. At the same time, the ratio of land to ocean on the surface of Kepler-452b should be different from that on the Earth. Consequently, chances are that this exoplanet may turn out to be a boundless ocean, dotted with archipelagos. If we leave the abstract figures for a moment, and try to imagine what life might look like on this amazing planet, so similar to Earth, and yet so different from it in so many ways, a truly fantastic sight will unfold before our eyes. The probable abundance of shallow, warm seas allows us to expect a great variety of aquatic life forms. from the smallest to the most impressive. As for land, there are likely to be stocky trees with thick trunks and stocky herbaceous plants. Because the spectrum of the parent star in this system is close to that of the Sun, the color of the photosynthetic parts of local plants is likely to be familiar to us, green or bluish. We can also expect a variety of small animals with sturdy bones and strong muscles. Another course evolution might take is creatures with an external skeleton, like terrestrial arthropods. As for flying creatures, the opinions of exobiologists are divided. Some believe that high gravity will be an insurmountable obstacle to flight, while others suggest that the high density of the atmosphere will be the decisive favorable factor in this matter. In any case, we still have many years of research ahead of us before we can say with any certainty that this planet is indeed suitable for life. Every year, we discover hundreds of new exoplanets. Some of them are forbidding and even dangerous, while others are very much like Earth. But no matter how much we observe other worlds, we cannot yet reach them. Earth remains our only home, and we must take every opportunity to preserve it. Every step along the path of progress leaves a scar on the face of our home planet. And it is hardly possible to say exactly when these changes will become irreversible. And let's keep in touch.